Hello, my name is Ed Wass. I'm a researcher here with the Center for Advanced Infrastructure and Transportation. Today we're going to show and give a tour of the Rutgers Asphalt Pavement Laboratory program. Take a walk. Alright, so here we are in our stockpile area. Typically the way things flow at the Asphalt Pavement Laboratory is we will go out into the field to a quarry, whether it's from northern, central, or southern New Jersey, and we typically like to keep stockpiles of each different size aggregate in-house. This way we have the material at hand. When a project calls for it, it's easily and readily available for us to come back, sample, and move forward with testing. Our stockpiles, once they are sampled, they are put into pans based on their aggregate size. From there, we will take these samples based on proportions and batch them out. Sort of like a baking or a cake recipe, a certain amount of a certain size stone, the next size, and we will put that all together into a weighed out sample in which we will then add the asphalt binder to that sample. Typically, once our asphalt samples are mixed, they are then placed in an oven here for a period of time to condition, bring them up to our compaction temperature. We then have a variety of asphalt compaction tools that we can use to shape our hot mix asphalt into various sizes. To my right here we call it our brick compactor. It makes a large brick type shaped sample that is primarily used for beam fatigue. Next in line we have our super paved gyratory compactors. These can be used to aid in super paved mixture design. We also use them heavily for performance testing, compacting asphalt samples to height. This is our ARC asphalt roller compactor. As you can see, it has a compaction head on the front of it, which simulates a roller in the field. It makes a large slab sample, as you can see here on our table. These larger slab samples can be used for a variety of things here at the lab. Most recently, we've been using them for friction and texture testing. So we have the ability to polish these slabs over time and look at the change in texture and the change in friction over the surface of the material. Another thing that we use that compactor for is for bond strength testing. So we are looking at a variety of asphalt tack coats and looking at their bond strength to one another. Behind me here is our asphalt pavement analyzer that's currently running. This is a testing machine that looks at the susceptibility to a mixture's susceptibility to rutting. What it has is 100 psi hose pressure along with a 100-pound wheel load that travels back and forth over the surface of cylindrical samples. You can see here in front of me two tested samples, one that has performed better than the other. There's no direct correlation to rutting in this machine to rutting in the field, but it gives us a good idea of a material's susceptibility to rutting if we are running comparison testing. So this is our coring and cutting, basically preparing compacted hot mix asphalt samples to move them over into performance testing. You'll see to my right we have a variety just of some examples of the sizes and shapes of samples that we end up compacting here at the laboratory and what their final product may look like before it goes over to testing. Here you have an overlay, here you have an AMPT, and here we have a beam fatigue sample.
Hi everybody, my name is Ed Haas. I'm in charge of all the performance testing here at the Rutgers Asphalt Pavement Lab. I'm excited to show you some of my equipment. So to get started, I'd like to show you guys our Hamburg wheel tracker. So this is a test that we use to test for rutting, which is how much the road deforms when you drive over it, and then also water susceptibility. So once we run them in here in a submerged state, these are some of the examples of our results. And you can see this one, it would be a better result. It didn't deform as much. This one a little bit worse because it did deform. And then you can see the exposed rocks here, and that's what we call stripping, and that would be an example of a failure that this machine's looking for. Alright guys, so the next piece of equipment I'm excited to show you is our asphalt mixture performance tester. And so what we do with this machine, since New Jersey has all 4 seasons and all different amounts of traffic depending on the time of day and everything else, this machine can then tell us what the stiffness of that material will be at every temperature and every possible traffic condition that we have. So this machine is very important when it comes down to quantifying our research. This green machine here is our compression machine, which you can find a version in every asphalt plant in the state of New Jersey. But the difference that we use here is we use a camera system, which then utilizes the video and AI to then go on and help us quantify the cracking while it occurs during the test. This piece of equipment is our bending beam fatigue, and what we use that for is to determine when cracks are going to start, or what we say is crack initiation. So all it does is it takes your beam and it bends it, so it clamps it in 4 spots, 2 on the end, 2 in the middle, and the middle moves up and down. And what ends up happening is, like, if you took a paper clip and bent it back and forth, when it starts to break, that's exactly what happens with the samples. So this piece of equipment is our overlay tester, and in the same way that the beam fatigue tells us when the cracks are going to start, this machine tells us how long it's going to take for them to get to the surface. So the way we do that is we glue a sample across 2 steel plates, and then the one plate stays fixed in the machine, and the other plate just moves in and out a little bit until the crack makes its way to all the way to the top, and that's when we would consider it a total failure. Okay, so this is our universal testing machine. Right now it's set up to run semicircular bend test, but it can also run for us our direct compact tension, or DCT, our ideal CTs, our poker chip testing, our low temperature IDT testing. So this machine can really do it all depending on how you configure it.
My name is Chris Erickson. I'm the manager of the Rutgers Asphalt Binder Laboratory here at Rutgers University.
All right.
So this is a bending beam rheometer. In almost all binder labs you're going to find one of these. So what this machine does is it tests beams of asphalt, very small beams, the same size as this steel beam that I'm holding in my hand. And we put it in the bath at very cold temperatures. This thing can go down to negative 30 degrees Celsius. And we test the beams in here, simple 3-point bend test. The stiffer the binder, the less it will deflect or bend. The softer the binder, the more it will deflect or bend. And you don't want a material to be too stiff, because out in the field, in real world scenarios, if the binder's too stiff in the wintertime, it'll crack. Now, if the binder's too soft, in the summertime, you'll get rutting. So there's a sweet spot between too stiff and too soft that we want the binder to be at. And what we're working on is something new in the industry. This is a tracking test that Thomas Bennett and myself have been developing for the DOT to look at different tack codes. And why that's important is that the state doesn't really look at the tack codes in terms of how well or how poorly they track. What I am standing in front of right now is actually a candy table. And you might be asking, well, what is a candy table doing in an asphalt laboratory? Well, candy table is actually an excellent table that we can use, and we can control the temperature of the table very accurately. And the reason why we want to do that is we want to simulate different road temperatures of when you would apply a tack code out on the road. And what we do is we have a 10-pound steel weight here with 2 gaskets on it, and we put it on a ramp, and we apply a tack coat in the middle of the table, and we roll the weight over the tack coat, and then we have a nice clean sheet of paper on the opposite side, and you can actually see how the material is tracking over time. And what I do is I take these sheets, and I actually use MATLAB, and I actually calculate how much is actually tracked on the pages, and therefore I can actually quantify the amount of material that is tracked on the paper over time.